Hi everyone. Today we will discuss elastic and inelastic collision. So here, as far as the collision is concerned, if you consider this chapter collision, so in this, the nature of collision, it can be when suppose two objects collide. So the collision, it can be one dimensional, it can be two dimensional. Now when we say this one dimensional collision, it means before the collision and after the collision, the objects or the particles, they are moving along the same line, the line of motion before collision as well as after collision, it remains same. So in that case we say it is one dimensional collision. Similarly, if you consider two-dimensional collision, then there will be change in direction before collision or after collision. So particles can move in different directions before collision, and after collision it can again move in some different directions. So that type of collision, it will be two-dimensional, provided those directions of motion are along x-axis as well as y-axis. Similarly, we can also have three-dimensional collision, but that generally occurs in case of space motion, where we have movement along x-axis, y-axis as well as z-axis. So let us start with this one-dimensional collision, and then we will discuss two-dimensional collision. So this is when we define one-dimensional or two-dimensional collision. This is with respect to their line of motion before collision or after collision. Now, depending on the nature of the collision, so we have again two different type of collision. One is termed as the elastic collision, another is termed as inelastic collision. Now, the basic difference between the elastic collision and inelastic collision is that in case of elastic collision, the momentum as well as the kinetic energy remains conserved. So in this elastic collision, sum of momentum is conserved as well as sum of kinetic energy is also conserved. Momentum remains conserved, kinetic energy remains conserved. Now momentum remains conserved in case of elastic collision because summation of all external force acting on the system, it is zero. As far as the collision is concerned, whether it is elastic, whether it is inelastic, whether it is one-dimensional or two-dimensional or three-dimensional, suppose, summation of external forces acting on the system, it is zero before collision as well as after collision. So this momentum always remains conserved in elastic collision as well as in case of inelastic collision, the momentum remains conserved. But this kinetic energy remains conserved only in case of elastic collision. This is a vector quantity. Momentum, it is your vector quantity, but kinetic energy, it is a scalar quantity. So here in this case, as far as the elastic collision is concerned, we have momentum as well as kinetic energy both conserved. In case of inelastic collision, momentum remains conserved, but kinetic energy is not conserved. There will be change in the energy before collision, kinetic energy before collision, after collision. Why these things happen, that we will discuss in due process. So let us start with this one-dimensional first in general, and then we will see each and every case separately. Now, if you consider this one-dimensional collision, so let us say before collision, there are two objects of masses m1 and m2, and m1 is moving with velocity u1 and m2 is moving with velocity u2 in the same direction. They can move into opposite direction, they can move in the same direction, and depending on their velocity, their direction as well as the magnitude of the velocity, the collision can take place. So here, if you are taking m1 and m2 moving along the same line in the same direction, so in that case, the collision will happen only when u1 is greater than u2. Then only this object will be able to approach this, so that there is a chance of collision. So u1 is suppose greater than u2, and after some time they collide. Okay, and after collision, suppose they collide somewhere here, and after collision, velocity of m1 it becomes v1, and velocity of m2 it becomes v2. So before collision, their velocities are u1, u2, their masses are m1, m2. After collision, their velocities are v1 and v2. Now, if we consider that it is a case of elastic collision, we are just assuming, just to justify, just to prove that. So in that case, we will have to check whether momentum as well as kinetic energy remains conserved or not. But if we assume, just for our understanding, that this is a case of suppose elastic collision, then we will have what? Momentum conserved as well as kinetic energy conserved. So if momentum remains conserved, so in that case you can say that summation of momentum before collision will be how much? m1 u1 plus m2 u2, because both are in the same direction, so the total it will be this plus this, so m1 u1 plus m2 u2. It remains conserved. So before collision momentum it will be same as after collision. So after collision it becomes what? m1 v1 plus this m2 v2. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is before. This is momentum conservation expression. Is this clear? Now let us consider that it is a case of elastic collision. So if we assume, okay, for our under, because exactly we don't know whether it will be elastic or inelastic, but under the assumption that it is an elastic collision, kinetic energy will also remains conserved. So we can say half m1 u1 square plus this half m2 u2 square is equal to half m1 v1 square plus this half m2 v2 square. So this is kinetic energy of the system before collision. This is kinetic energy of the system after collision. So half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus this half m2 v2 square. So that way we can consider this kinetic energy conservation. I hope this is clear. So here you can see this expression. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So this way we can consider this. Now here also you can see this is under the assumption that collision is elastic. Till it is not known to us that whether it is a case of elastic collision, we can't consider this. But this relation is always valid, whether it is elastic collision or whether it is inelastic collision. But this you will be able to use only if it is known to us that the nature of collision it is elastic. Now you can consider this two-dimensional collision. Now if you consider the two-dimensional collision, the only change, whatever we have discussed is, this example, the previous example that we were considering, it was one-dimensional. Before collision and after collision, the line of motion, it was along the same direction. Now we will consider the two-dimensional collision. Suppose some object is coming from this side, some object is coming from this side, and they collide. Okay, after collision, one has moved in this direction, another has moved in this direction. So this is the most general form of the two-dimensional collision. Before collision, the particles are along two different directions. After collision also, they get diverted along two different directions. Then how to consider all these concepts? So here if you see, suppose this M1 before collision, it is moving in this direction, and when we say it is moving in this direction, so it is at an angle of alpha. Okay, this angle is alpha. Again, M2 is moving in this direction, which is at an angle of this beta. So it means before collision, M1 is moving at an angle of alpha with the x-axis, M2 is moving at an angle of beta with the x-axis. After collision, somewhere the collision takes place, and then after collision, M1 has started moving at an angle of gamma with the x-axis with the velocity v1, and M2 with the velocity v2 at an angle of delta. So again here, we will first consider that conservation of momentum remains conserved. So when conservation of momentum we are taking, it is applicable whether it is elastic or inelastic. But again, if we assume that it is also a case of inelastic collision, then again we will consider the kinetic energy conservation. So first let us consider the momentum conservation, which can be considered in any of these cases. Now momentum, it is a vector quantity. So momentum remains conserved. This means this implies that momentum along, summation of momentum along x-axis is conserved, as well as summation of momentum along y-axis is conserved. This is a vector quantity, so we will have two different components of this because it is two-dimensional case. So summation of momentum along x-axis is conserved, as well as summation of momentum along y-axis is conserved. Now under this assumption, so summation of momentum along x-axis, when all velocities we will consider along x-axis, that will give us the momentum along x-axis. All velocities we will consider along y-axis, so that will give you the momentum along y-axis, and then we will form the equation. So here, before collision, velocity along x-axis is how much? u1 sine alpha. Now see this particle is moving in this direction. It is moving in this direction, and this angle is alpha. So what are the components? u1, this is u1. So its component along this direction, it will be u1 cos alpha, and along this direction it will be u1 sine alpha. Because this is this side, this angle is your alpha, so this component will be u1 cos alpha, and this component it will be u1 sine alpha. So momentum along x-axis of this object, it will be how much? m1 u1 cos alpha. This u1 cos alpha is along positive x-axis, so m1 u1 cos alpha is also along the positive x-axis. m1 u1 sine alpha, it is along the negative of y-axis. So momentum of this along y-axis, it will be m1 u1 sine alpha. Similarly, of this object, if you consider, this is moving in this direction at an angle of this beta. So this object m2, before collision, it is moving at an angle of beta. So this component will be how much? This is u2 cos beta, and this will be your u2 sine beta. Okay. So this component of momentum along x-axis, it will be m2 u2 cos beta, and this is m2 u2 sine beta. So here you can see this is positive, but this component is negative. Here both are positive. This is along positive x-axis, this is along positive y-axis. So m2 u2 cos beta, m2 u2 sine beta, both are positive. Now let us develop the expression as far as momentum along x-axis is concerned before collision. So here, if you consider, can we consider this way? Momentum along x-axis is conserved. So summation of momentum along x-axis is conserved. So m1 u1 cos alpha plus m2 u2 cos beta. These were its x component along x-axis of m1 as well as m2, and both were along the same direction. Here you can again see this. u1 cos alpha this side, okay, and u2 cos beta this side. So m1 u1 cos alpha plus m2 u2 cos beta. This was momentum before collision. After collision, this is moving with velocity v1 at angle of gamma. So this component will be how much? v1 cos gamma. This is again along the positive x-axis, and again its y component will be what? This side, v1 sine gamma. So v1 sine gamma. So again this is positive and this is positive. V2 it is at an angle of delta. So V2 cos delta and V2 sine delta. V2 cos delta as well as V2 sine delta. So this is again along positive, and this is again along negative of this y-axis. So again you can see all these expressions. So this was positive, u1 cos alpha, u2 cos beta was also positive. So this is with the positive sign, this is with the positive sign. V1 cos gamma, it was also with the positive x-axis, and V2 cos delta is also with the positive x-axis. So this is positive and positive. Now summation of momentum along y-axis. U1 cos alpha, it was what? Negative, because this was the direction of U1. So this was positive, this was negative. So minus of m1 u1 sin alpha, because this is along negative of y-axis, so it is minus of u1 sin alpha, and that's why it makes its momentum negative, minus m1 u1 sin alpha. Beta it was along this direction. So this component and this component both are positive. So u2 sin beta. So this is with the again positive sign. V1 sin gamma. Again V1 sin gamma. V1 it was along this, and this angle is your gamma. So this is positive and this is positive. So V1 sin gamma. Delta it was along this direction. This angle is delta. So again, if you consider this will be positive and this is negative. So this is negative. So depending on that, we have taken summation of momentum along x-axis conserved, that gives us m1 u1 cos alpha plus m2 u2 cos beta is equal to m1 v1 cos gamma plus m2 v2 cos delta. Similarly, momentum along y-axis conserved, that is minus of m1 u1 sin alpha plus m2 u2 sin beta is equal to m1 v1 sin gamma minus m2 v2 sin delta. So this is from the momentum conservation. Now, if we again assume that this is a case of inelastic collision, so under that assumption again, repeatedly I am saying this you can use, only clearly it is known to us that the collision is either elastic and inelastic. If it is a case of elastic, then we will consider the conservation of kinetic energy. If it is inelastic, then you can't consider this. So again, if you assume that this collision is also a case of elastic collision, then the kinetic energy will remain conserved. So in that case, before collision, the kinetic energy what? Half m1 u1 square plus half m2 u2 square. Now you can see why we are not taking consideration of the directions alpha, beta, gamma and delta. Just because kinetic energy is a scalar quantity. So it does not depend whether the particle is moving at an angle of alpha, beta, gamma or delta. So the total kinetic energy of u1 before collision, it was half m1 u1 square, because it is a scalar quantity, so it does not depend on this angle. So it is simply half m1 u1 square. Of mass m2, it was half m2 u2 square. Similarly, after collision, it is how much? Half m2 v1 square, half m1 v1 square plus this half m2 v2 square. Half m1 v1 square of the object of mass m1 moving with the velocity v1 after collision, and of m2 moving with v2, it will be half m2 v2 square. So this becomes your half m1 u1 square plus this half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So this is the kinetic energy conservation. Now you have these three equations. We have momentum along x-axis conserved, momentum along y-axis is conserved, kinetic energy remains conserved under the assumption that it is a case of elastic collision. So we can use all these relations. So we have discussed all this as far as the one-dimensional and two-dimensional collisions are concerned, and the nature of the collision, that is elastic and inelastic collision. There will be different cases of this. We come across a term like coefficient of restitution and all that. So we will discuss in the next video. Thank you.